Hi, everyone. I'll provide the brief introduction and then everyone will describe the results in the group. So we were exploring turbulence statistics in nearby molecular clouds using spectral line data cubes. And specifically, the group was looking at Ophiuchus, Perseus, and Orion, three very nearby molecular clouds in their 12CO and 13CO 1-to-0 transitions. So each pixel in these maps has an associated spectrum, and we can use that spectral and spatial information to infer turbulence properties in these clouds. So the purpose of the project was to be exploratory. So everyone looked and used slightly different methods to compare turbulent properties between the clouds and within them to see how they vary. And so with that, I'll let everyone take it away.
There's various methods to quantify the turbulence statistics. And the first one is using the spatial power spectrum. And here I calculate the turbulence statistics for using the 12CO molecular maps. And to do that, from the molecular maps can be converted into the 2D power spectrum using the Fourier transform to get the 2D power spectrum, and then reduce to the 1D power spectrum. And we do that for three different molecular clouds. They are Orion, Ophiuchus, and Perseus. And from the slope of the 1D power spectrum, we can derive the turbulence statistic, which is related to the spatial information of the molecular clouds. And after that, we compare between each pair molecular clouds, and we found that the pair of Orion and Perseus having the similar turbulent metric, distance metric. And the other methods is the spectral correlation function, in which we aim to quantify the correlation between the spectral structure with the spatial density structure. And to do that, we calculate the correlation between the cups vary with the spectral dimension to create the 2D correlation surface. And after that, from the correlation surface, we can convert into the we convert into the 1D. We fit with the power law and then derive the turbulence statistic, and we compare between two pair of molecular clouds and found the distance metric between those pair of molecular clouds.
Hello everyone. So I hope I'm audible. I'm Fazlur Rahman. As a continuation of what Lee was speaking, so since the project is exploratory, so what Lee was trying is with 12CO, but what I tried is with 13CO. We studied different molecular clouds, Orion, Ophiuchus, and Perseus, and my focus was to study the how spatially the properties are varying. For example, the spatial statistics correlations. So in the beginning, we started with probability distribution function, so Debstat can compute them, and we found that as expected, these are following log normal distributions. So these are for Orion, you can see my cursor, Ophiuchus, and Perseus, and to quantify how much they are deviating, among the clouds, between the clouds. So what we have done is we have this statistic called log normal distance, which is given by the width of each PDF. So we find that the Orion Ophiuchus has this log normal distance 53, and these are the three numbers. So probability distribution function is a 1-point statistics, so it's not complete. So we have to check as Lee was doing, we have to go to the power spectrum, which is the 2-point statistics, I mean the Fourier transform of the 2-point correlation function. So as a continuation of what Lee was showing, so we computed, I have computed the power spectrum for Orion, Ophiuchus, and Perseus, and it's following a power law, and we fitted it with a power law. So I have given for each cases, we have computed 1D power spectrum as well as 2D power spectrum, and the numbers I have shown here are the slopes for the 1D power spectrum, which the fitting can be seen here. So to quantify to compare how deviating or how similar two clouds are in terms of the slope of the power spectrum, so we have some quantity called SPS distance, power spectrum distance, so given by this equation. So as Lee was showing, Orion and Perseus, it's coming to be closer. I mean, the value is very small, which implies that they are similar, and we find a very large difference between Ophiuchus and Perseus. So again, power spectrum is not complete as the distribution is not Gaussian, and power spectrum cannot capture the phase information. So we have to go to bispectrum. So we did some preliminary calculations of the bispectrum for each clouds, and we find that the off-diagonal terms are not zero, and we can see that there is drastic difference between each clouds in terms of bispectrum, which means that bispectrum and higher order correlation functions and higher order statistics are important. So over to the next speaker.
Thank you very much. So now we are getting focused to the investigation of the shape of the probability distribution function, taking into the account that we are right now getting focused on the comparison of two different traces, 12CO and 13CO, in the three different clouds, Ophiuchus, Orion, and Perseus. What we did, we calculated the PDF distances in three different methods. So right here, you can see the third result for the third method, the log normal distances, which is a parametric method. And we found out that the largest number for the log normal distance is for Perseus. Right here, you can see that the PDF profiles for different molecular clouds, and the empirical cumulative distribution function for each of them. It is simply giving us a difference between these two tracers. You know, we are simply looking at the differences between these two tracers, 12CO and 13CO. In the second slide, you saw that how 12CO is actually tracing brighter regions. It actually traces, it actually shows 10 times brighter values than 13CO. So we can see how turbulences statistics can vary and change between these two different tracers. So right now, the result is showing that the differences in scaling for the Perseus, which is showing a larger number as in log normal distance, which is showing a differences in scaling between 12CO and 13CO. And what we are measuring as a difference here is actually related to the differences in the width, the log normal width of 12CO and 13CO. So in the big picture, putting all these results, we can somehow have the big picture of how turbulences statistics would vary between tracers, different tracers, or different clouds in general. Thank you very much.
Thank you.
Okay. Hi everyone. In this project, I'm responsible for investigating the turbulent statistics in star-forming and non-star-forming regions in Orion. So on the left-hand side, you can see two projected 2D images of the star-forming region and a non-star-forming region in Orion. These are traced by 12CO. And based on these projected image, we can calculate the spatial power spectrum of these two images. So in the middle panels, you can see the spatial power spectrum and the slope fitted to the curve. So in the star-forming region, the power spectrum gives us a slope of -3.7, while in the non-star-forming region, the slope is about -4.7, 4.3. So we don't see a huge difference in these two regions. So we move on to the to calculate the spectral correlation function. The spectral correlation function also considers the velocity at the third dimension. The slope in the spectral correlation function in the star forming region is about minus 0.18, while in the non-star forming region, the slope is only minus 0.09. You see a huge difference between the two methods. The two methods give us different comparison of the same data cube. So different statistical methods would probe the different aspect of the data. That's the basic conclusion here. Okay, thank you.
I'm sure we're out of time, so we'll have our summary page.
Okay, thanks.